All right. First of all, as I'm looking at units here, the metric system in this case, this is at Wikipedia in the sciences and math. That's what I teach, physics, astronomy, math. I totally trust Wikipedia as soon as someone tries to take out a fact, because that's what sciences and math are based on. It's very quickly fixed. So here's International System of Units. We use also a different word for it, metric system. There we go. And it starts focusing on the 7 base units that we have, meters, second, kilograms, and then we get into thermodynamics, which is the mole and the Kelvin, and then we get into electricity, which is the ampere, and then into optics, which is light intensity, which is the candela. Sounds like candle, right? So I'm going to scroll a little bit down. Anything else besides these base units, combinations of them are called derived units, and here are the base units again, by the way. And here are the derived units, and of course there are lots, and you would have the same in the American system. So for example here, force weight, which is the Newton. Notice that this is combined here, kilograms meters per second squared. I didn't mean to scroll here. And in the American system, well, that would be the pound, and it also would be a combination of slugs times feet per second squared, that kind of thing. Or if we find somewhere here, acceleration should be somewhere on here, except I don't see it right now, or velocity, we would have meters per second versus feet per second, that kind of thing. So these are derived units and the base units in the metric system or the International System of Units. All right, a little bit more here. These are the prefixes that you might be familiar with. So here's the kilo, for example, which means 1,000. We don't really use the mega a lot. We just call it 1,000 kilometers kind of thing. We would never call it megameters. And then there is the centi here, or the milli, which we use for centimeters and millimeters. Just makes it easier to work with numbers that are nicer if we reduce the unit to centimeters or millimeters or centiliters, that kind of thing. This is actually from my first physics lecture that I give in my physics class. So how did the base units originate? I highlighted these 7 over here. I'm just going to go over the first 3 here. So the meter originates from going from the equator to the pole, apparently through Paris, and dividing that by 10 million, that's where you get the meter, or divide by 10,000, that's where you get the kilometer. Looks a little cumbersome because you're really not going to walk that way, but you can use that anywhere on Earth, that particular measurement. The foot, on the other hand, well, yeah, it's nice, there's a foot, but everyone has a different foot. So that one is one measurement that can be used all over the world, and yes, you're not really going to do it. It's actually an astronomical measurement, or surveyors would be figuring that out using actually astronomy for that, and that's how you get the meter. And then there is the prototype, which is, I believe, over here, where that would be exactly 1 meter long. And then you get the meter, so you divide that by 10 million. Now you get the meter. You divide the meter by 10, you get what's called a decimeter, respectively, that's 10 centimeters. You make it into a cube, which is 1 cubic decimeters, or 1,000 cubic centimeters. And we give it a new name, we call it a liter. We fill it full of water, and that amount of water that we have in there, exactly 1.0000 liters of water, is defined as 1.0000 kilograms. That's how the kilogram is defined, through the meter with the density of water. And that's also why it's not surprising to find in the metric system that the density of water is exactly 1.0000 grams per cubic centimeters, or 1,000 exactly kilograms per cubic meter. So that's the history for both the meters and the kilograms. The second, well, take the length of a day, divide it into 24 hours, divide it into 60 minutes, divide it into 60 seconds, respectively. Just divide the whole thing by 86,400. There's the second. And notice that this one really starts out not kind of nicely with decimals or metric, but at the end we still get the 1 second based on a measurement that anyone can take in the world. Let's see, this one is a follow-up about the other units in a metric system, but I'm just going to go on here to the imperial system or American system. So F for the foot, just like it sounds. There it is. That's, for example, here. Take these people out of church, 16 randomly chosen, and you get the rod, I guess, and if you divide by 16, hey, you get the foot, an average foot, right? The seconds is the same. Divide by 24, 60, and 60, or divide by 86,400, and you get the seconds. In a pound, you would actually have to, I got this here from the Wikipedia, and it's actually a little bit confusing. There's really, historians cannot really say, where did we get the pound from? But anyway, it's out there. By the way, when you abbreviate it for the plural, it's still LB, not LBS, it's actually LB in the plural, because it comes from the Spanish libre, which already is pounds in the plural. All right. So here's what I call quickly the American system. Its real name is the United States Customary System. A little bit of a long word. I think that might have been the first that I used. I really try to avoid that when I record. And we can see that it's only really used in the United States, Liberia and Myanmar. Everywhere else you have the metric system. And I guess Canada and Great Britain are a little bit of a mix between those. All right, so remember that for the metric system, it's pretty much start with the base units and then get to the derived units. You have these in the American system as well. For example, here's the inch. Then there's another, I should stop doing this. And then somewhere you find here the pound or the slug actually. But you also have a lot of these derived, not even derived units, but units that are related to them, but they have these really strange conversion units, such as 5,280 feet in a mile, or 1,760 yard in a mile, or 3 feet in the yard, or 12 inches in the foot. And that just goes on for all these kinds of units. Here are areas. Look at all these screen numbers in the metric system. You just multiply by 1,000, multiply by 1,000,000, divide by 1,000,000, that kind of thing. So here in this particular one, they're not focusing on all these units. They're focusing on how to convert between the different kind of volumes that are there. And that, of course, makes it quite a bit harder in the what I call the American system. By the way, there are actually exactly 231 cubic inches in the gallon. I learned that not too long ago. All right, that's basically it, what I want to say here. So this is actually the OpenStax textbook that we're using. I believe this is chapter 9 for measurements. It took me a while to catch on here on the sign here that this is Finnish. I've been there once a long time ago. And here you have kilometers. You can kind of see it hidden here, and then they left it out here. They assume that people know it as kilometers. Notice the comma here. In the United States, we use actually a period there, so it would be 0.5 kilometers. For some reason, in Finland, apparently, in Germany too, we use 0.5 kilometers. I do like the point better than having a period there, because it's a real break in between this many kilometers and this many parts of a kilometer. All right, gotta go beyond this image here. All right, some cheese here. They show here that you have on the scale kilograms and pounds. Notice 5 kilograms, 11 pounds. This must be an American scale, as there is 2.2 pounds to the kilogram. The two shouldn't be confused. Actually, kilogram is a mass. Pound actually is a force or a weight. By the way, as the pound is not being used in Germany, for example, anymore, you can still actually go to a store and ask for 10 pounds of potatoes, and you will get 10 pounds, which is 5 kilograms. Notice that there's a conversion factor of 1 to 2 for the so-called German pound, which technically doesn't exist anymore, but we still use it. All right, scroll down a little bit here. I'm going to go all beyond that. You will find quite a few conversion calculators online as you need them. This apparently here is on Google, and they're pretty good. Just Google the right thing, centimeters to inches or something. Let's see, I'm going to scroll through here, and oh, yep, there we go. So that's a little bit of history trying to implement the metric system in the United States, and as you know, as you see, it failed. However, since 1992, it is actually the system in the United States as well. It's just that we don't use it in everyday life. And here what I highlighted, so there was a decision followed intensive lobbying by American businesses whose factory used machinery designed to use customary measurements by workers trained in customary measurements. And I kind of agree with that. Yes, you would have to retrain everyone, and that costs a lot of money and resources. But on the other hand, because the metric system is so much easier, multiplying by 10 or 100, divide by 100, divide by 10, and so on, the conversions are so simple, it really isn't that hard. On the other hand, if you continue doing that, which we've been continuing doing that for decades, for centuries now in the United States, using the American system where you have these strange conversions, well, you make mistakes. And you always need some table and some calculator. You cannot just shift the decimal point. And that is actually cost the American economy quite a bit of money. So to me, that really is not the greatest argument. Yes, there is some truth behind it, but it really costs the American economy a lot. And there are lots of American businesses that actually use the metric system. Okay, there's a second sentence that I highlighted here. There was also intense public pressure from American citizens who didn't want to go through the time-consuming and expensive process of changing the country's entire infrastructure. What I'm thinking about here are, for example, road signs. Okay, yes, it would cost money, but it's a one-time thing. You would only do it once. What I really disagree with this particular sentence, intense public pressure from American citizens, is that in our everyday life, it really doesn't matter if we use miles or kilometers, if we use pounds or kilograms, it really doesn't affect us much. The ones that are really affected by it are the ones who deal with measurements every single day in their job, like myself, teaching physics and math. Someone working in a factory, someone working in a hospital, someone working in technology, where they have to make all kinds of conversions, and they are really appreciate the metric system. So this particular one is really not a good argument for me to keep the metric system out, because in our everyday life, if we measure the distance in kilometers or miles, no big deal, doesn't really matter. So might as well go with the kilometers and the meters and the grams and the kilograms, because it's the other people, it's the people who work in the industry that really need that. All right, talked enough about this. Going to scroll down here, and we are at the problems here. I'm just highlighted a few here. Which metric base unit would be used to measure the height of a door? Well, meters, about 1.8 meters, 2.0 meters, that kind of thing. Which metric base units would be used to measure your weight? Kilograms. Okay, here I need to point something out. I think I have that somewhere here. The kilograms versus the points. Oh, I think it's going to come up. I'll do that later. So kilograms. And then here, for following as determine the base unit metric, choose from liter, gram, or meter. The word I disagree with here, by the way, it's not a base unit, because the meter is, but the liter and the gram are actually derived units from the meter cubed, respectively, from the kilogram. Shift the decimal point. Amount of soda in a bottle, well, that would be in liters. Weight of a book you're mailing, well, that would be in grams. Amount of gasoline you need to fill a car's tank, well, it would be in liters. Height of computer desk, meters, and so on. All right, go to the next section here. All right, let's see. And again, I'm going to scroll down to my highlights. So apparently this is about area, and I really haven't highlighted much at all here. It's just, there's a lot of computations in here, and notice that I do this particular unit a little bit different with all these regression curves and measuring and so on. So I can skip quite a bit here. For the following exercise, determine the most reasonable value for each area. Bedroom wall, that would be in the neighborhood of 12 square meters. For example, 4 times 3 square meters, which is about 12 by 9 feet. That sounds about right. City park, Actually, it's the 1,200 square meters, which is actually a small one. It's about the size of just 10 houses. 1,200 kilometers, by the way, is way too big for a city park. So I would even say that this one is a little bit small. Kitchen table in the neighborhood of 2.5 square meters. This one here, by the way, would be in the neighborhood of like 1 square inch or a little bit less. So it's ought to be 2.5 square meters, which is about 25 square feet. That's 5 by 5. That's a pretty good size table, yeah. All right, and then here's some more such exercises. And notice I'm going through these here actually pretty quickly, except for what I did earlier about what I think about that it should be implemented to the metric system in the United States. All right, let's see, scrolling through here. So this is volume. Notice they don't do everything here. They don't even do the derived units, so they just throw this at us. So for following is to determine most reasonable value for each volume, I will go with the 50,000 cubic centimeters. Here, if I take the cubic root of this one here, which even for me is a little bit hard, it's going to be 10 times 10 times 10, a little bit more maybe. So 20 times 20 times 20, 20 centimeters, that's going to give me in the neighborhood of 8, that's only 8,000 cubic centimeters, by the way. So I make it 30. That's 27,000 cubic centimeters. So that's about a foot by foot by foot. That kind of sounds like a terrarium, right? Milk carton, that was the again. Should really get rid of it. 236 milliliters, large fraction of a liter. That would be a milk carton. Box of crackers, neighborhood of 1,500 cubic centimeters, probably 10 times 10 times 10. Yeah, that's about 4 inches by 4 by 4 inches. Yeah. All right. So here we have grams and kilograms. Here I highlight a little bit. All right, so I'm going to read the highlighted part. Any discussion about metric weight must also include a conversation about mass. Scientifically, mass is the amount of matter in an object, whereas weight is the force exerted on an object by gravity. So weight and force take on the same units. The amount of mass of an object remains constant no matter where the object is. And then, since there's no easy way to measure mass, and since gravity is just about the same no matter where on Earth you go, people in countries that use the metric system often use the words mass and weight interchangeably. But scientifically, the kilogram is only a unit of mass. In everyday life, it is often used as a unit of weight as well. And that, in my opinion, is unfortunate. We do that mistake, for example, in Germany, where we use kilograms correctly for the mass, but we also use it for weight and even for force. And it bugs me because it's not. It's the Newton. However, we actually do the same problem, the same mistake in the United States. We use pounds for force and weight, which is correct. It is a unit of force, but we also use it for mass, which is not correct. It's actually in the American system the slug, perhaps a unit you have never heard of before, and it spells like the animal slug. There it is. And oh yeah, my Google on my browser and on my computers is in German. All right, but I got to the English one here, so I click on slug, this ambiguation, and I'm going to go to, hopefully very quickly, I don't want to waste your time here. Where'd it go? There it is, slug unit. There we go. So the slug is a derived unit of mass system of measurements in the United States customary measurement system. So this one, if you look at this one here, slug unit, in the American system, it's actually not the pound that is the unit for mass. It's what's called the slug. It's actually relatively big. Somewhere here it says 14.6 kilograms, respectively 32-pound mass. If we want to use mass, we ought to put a little m there for next to the pound. So that's the slug. Back to this one here. So yeah, we make that kind of confusion between mass and weight in both mass, weight, and force in both systems of measurement, at least in our everyday lives. In physics, I always pay attention to it. Obviously, kilograms is mass, newtons is weight and force. And what they also say here, no matter where you are on Earth, well, if you have 2 kilograms here, which is about 4.5 pounds, or about 20 newtons, well, anywhere else on Earth, the same 2 kilograms is still 2.5 pounds and 20 newtons. So they're kind of a little bit interchangeable because we're almost all the time on the surface of the Earth. All right, scroll down here. Again, here for following is to determine the most reasonable value for each weight. Aspirin tablet, 300 milligrams, so a fraction of a gram, which is also a fraction of an ounce. An elephant, yeah, let's go with 5,000 kilograms, which is about 10,000 pounds. A baseball, 145 grams, which is in the neighborhood of, is it 6 ounces, 5 ounces maybe. An orange, also 115 grams, that looks like 4 ounces. A pencil, 6 grams, that's kind of like a fraction of an ounce, like a quarter. An automobile, 1,300 kilograms, that's in the neighborhood of close to 3,000 pounds. All right, let's see if this was the last unit, or if I have another one here. Nope, temperature, there we go. So temperature, Celsius, Fahrenheit. I have posted another video that I'd like you to watch for just a minute, where the instructor actually tells us, hey, there is an advantage for the Fahrenheit scale. To me, there really is no advantage or disadvantage between the two, because we're not converting from the Celsius to something else. We're not converting from the Fahrenheit to something else. We don't have strange conversion factors like 12 or 3 or 16, that kind of thing. We don't have them in the Fahrenheit. It's just Fahrenheit from 0 to whatever, and then into the negatives. Celsius, the same thing. Of course, we do have the scientific one. The Celsius isn't the scientific one either. It's the one we use in everyday life. It's actually the Kelvin that we use in science. And if we are in the American system, where we also wouldn't then use the Fahrenheit scientifically, we would actually use the Rankine. And the Rankine and the Kelvin both have the advantage that they have 0 kelvins being, or 0 Rankines being, the coldest temperature possible. So, yeah, and then this one here, I would almost call this one here, the sun, I would tell it in kelvins, which is 5,300 kelvins. Actually, 5,700 kelvins. All right, again, let's see what I have here. Determine the most reasonable value for each temperature. 37 Celsius, ice cube, 0 degrees Celsius, boiling water, that's 212 Fahrenheit or 100 Celsius. On a summer day, 23 degrees Celsius, yeah, 70 degrees, 75 degrees Celsius, that's in an oven. That's almost boiling water. Winter day, yes, 3 degrees Celsius, that's actually still above freezing, because 0 degrees Celsius is the freezing. Lava, 700 degrees Celsius, which is in the neighborhood of a little bit of 1,000, maybe 1,500 Fahrenheit. All right, let's see if there is one section left. I don't think so. Nope. Oh yeah, and this is what we had earlier. The meter, the kilogram actually, and then the other is the temperature, which would be kelvins technically, and the mass, which would be kilograms. All right.